So let's finish this thing up. So what we determined two different ways here is that the acceleration due to point G there is 0.201 meters per second squared. Now the next thing to do is to check the assumption that went into that. And the assumption that went into that is that the roller doesn't slip. Okay, so that's what we'll do next. So what we want to do is to find what the friction would actually be to make this system work. And what we did there, when we did this first analysis, and we did two different equations, sum of fx is magx and sum of mg is ig alpha, is we got ourselves a nice easy relationship there between force of friction and agx. So the force of friction is 408 agx. That's what's going to be required to generate the right amount of friction so that there's a correlation between A and alpha. So what we can do is figure that out, because we know what agx is now. It's 0.201. So 408 times 0.201 is 82 newtons. So friction has to be at a minimum 82 newtons so that this thing won't slip. If it's less than that, we'll start kind of dragging the roller across the ground without it rolling. Okay. Now, this is actually static friction here that we're looking at, because if the rail doesn't slip, the velocity down there will be 0 at any instant. So that's static friction that acts at the bottom of the wheel. So we'll analyze force of friction as mu Fn. All right, so now force of friction is mu Fn. What that is, that gets us the maximum possible friction. For part 1, we've got mu at 0.37. All right, so that's the static frictional coefficient. So friction can go as high as 2,976 newtons in part 1. All it needs to go up to is 82.1 newtons. So the no slipping assumption is fine. There's lots of available friction there to prevent it from slipping. It only needs to go up to 82.1 newtons to make this system function properly, and it can do that. So the no slipping assumption is correct. All right. So what you would then do would just be to realize your acceleration of g in the x direction is 0.201. Use a constant acceleration equation and figure out the velocity. It's about 1.01 meters per second when t is 5 seconds. Okay. Now for part 2, it's the same problem, just with different coefficients of friction. They're greatly reduced. So what we would do is we would come up with the required friction, which we did already. It's 82.06 newtons. You know, we did that previously. That was independent of the coefficient of friction. That was just plugging into this relationship right here. But on part 2 then, when we check to see if we can generate that much friction, we take the static coefficient, 0.008, times the normal force, and we get 64.34 newtons. Well, that's not enough. We need 82.06. So slipping is going to occur here. We're going to essentially drag this wheel, at least for some of the time, across the ground without it turning. Okay, so if that's happening, the force of friction then is mu Fn. Now we have to change mu to the kinetic friction, because now it is slipping. The velocity down here is no longer 0, so we don't use static friction. Once it starts slipping, you use kinetic friction. So the actual friction there is 56.3 newtons, based on the kinetic coefficient. Then what you can do is do F equals ma with 56.3. If the roller is slipping, it's actually a much simpler problem, because it's just sum of F equals ma. We got the component of the 250 newtons there to the left, the friction, which is mu Fn to the right, because we're overcoming it. We're pushing friction to its maximum. It's mu Fn value. And that's going to equal ma. You can solve for a. It's 0.233. Okay. So there's an example of that. We've got some homework here. 351, 353, 354 due next Monday with the final, the 11th. Okay. All right, now let's have a look here at a handout problem that I'd like to look at here. This will help review some of the stuff for the final. All right, so we're going to look at this one right here, door swing 1. It's under the homework downloads. So why don't you download that one? Okay, so it's under the homework downloads. Door swing 1. So what we have here is a problem with a door. And what we're going to do is push on the door with 30 pounds on the outside push plate there. So the door itself is 4 feet by, I think it's 7 feet, 2 hinges. And we're going to push on it with 30 pounds. And it's going to swing open, of course. Now, we want it, for safety purposes, the doors to open no more than 70 degrees. And I'm going to change the 1 second in your handout. I'm going to make that 1.4 seconds. You want to figure out what's the required weight of the door so that it doesn't open more than 70 degrees in 1.4 seconds. And also, for that weight, what are the static reactions at each of the hinges and the dynamic reactions at each of the hinges? And that'll go, so this will be 1.4. Okay. So by static reactions, I mean the reactions if the door is just sitting there without moving. That is basically using statics to find these reactions. Dynamic reactions would be the reactions caused by the acceleration of the plate, both normal and tangential. Or excuse me, I call it a plate, it's a door. Okay. All right, so to do this, let's kind of start looking at this thing. Now this is a kinetic problem. We've got motion and acceleration and moments and alphas and that sort of thing. There's 3 types of kinetic problems we've gone through now. Translation, fixed axis rotation, and free plane motion. Now this thing's rotating about the hinges, so it's fixed axis rotation. So these are the elements that we're going to start off with. Moments, alpha, and I. Okay. So we're going to want to start working with these things. Now the moment is pretty straight up because you're pushing on the thing with 30 pounds. It might be easier to visualize this problem from the top, looking down at the door. You can do it that way for a lot of it. Not the static reactions, but pretty much everything else you can do that way. And this is what you'd see. You'd see this door. We're going to keep the 30 pounds normal to the door on the push plate throughout the entire motion. So we got the moment pretty well figured out there. Now we don't know the mass yet, so we don't have I. But I think we can get alpha, okay? Now, stay in the native unit here for dynamics equations. Degrees don't work. You got to be in radians. 70 degrees is 1.22 radians. All right. So what we got here, we're opening 1.22 radians in 1.4 seconds. Now I've changed that. We realize that we've got motion, acceleration, moments, things like that. So we know we're doing kinetics. There's 3 kinds of kinetics. And this isn't translation, and it's not free plane motion. It's rotating about the hinges. So it's fixed axis rotation. So we're kind of narrowing in on how we approach this, okay? And I think what we want to do next here is find alpha. So why don't you pause here and see if you can find alpha. Now, just a hint on that. Don't try and do m equals I alpha yet, because you don't know I yet. You got one unknown in there. You can't have a second with alpha. Figure out a different way to get alpha other than m equals I alpha. Okay, so you've paused, and now we'll start up again. So let's have a look. All right, now here's how you get alpha. See, you can use a kinematic equation. Theta is theta 0 plus omega 0 t plus 1/2 alpha t squared. You know how far it's got to open, and you know how long it can take. So when you work that through, you're going to get 1.25 radians per second squared. That's alpha, and that's constant. The moment then is 120 foot-pounds. So the next thing to do is to find the moment of inertia. All right, so see what you can do on that. You might pause for a minute, then come back. Work on it yourself a bit. All right, let's have a look at finding the moment of inertia. So to accomplish that, what you're going to do is you'll take moments about A and set that equal to IA alpha. Okay, because we got the moment and we got IA, or excuse me, we got alpha. You can just back in and find what IA is. Okay, so there's the moment of inertia. Now the last thing to do here for this first part of this, we'll work some more on Wednesday on this, is to figure out how to analyze I for this thing. Now you are going to find IA over here on the hinge line. That's what you want to do. So you can handle this two ways. You can treat it like a plate, and you're going to want to, if you do that, you're going to use the transfer axis theorem and use this axis that I'm coloring in now through the center of gravity, and then work that over to the hinge line, which would be your axis. You can also treat it like a slender rod and just go with ml squared over 3, because you're taking moments of inertia about the far side there. So there's a special equation for a slender rod that you can do that with, okay? So you can go either way. You know what IA is. See if you can back into the math. So you can go IGX for a plate plus MD squared, or you can go IAX is ML squared over 3. See what you can do for the mass on this. So we're going to find the required mass next. I've got another video here. It might be kind of repetitious with this one, but I had some problems, so I'm kind of splicing them together. So there's one more video on this after this one.